Let's get started with chapter 5. This is a very, very important chapter. We're going to talk about control volume approach to understanding fluid dynamics, and we're going to apply it to the continuity equation and and get a description for how mass moves around in flow fields. So if we look at the roadmap and the learning objectives for this chapter, we can see that the chapter describes how conservation of mass can be applied to a flowing fluid. The resulting equation of conservation of mass is the continuity equation. And this continuity equation it can be applied to a spatial region called a control volume, uh, which is also introduced in this chapter and is extremely important for the next couple of chapters because we're going to apply the control volume approach to not only mass and continuity, but also to momentum and energy in the next two chapters. But before we do that, we're going to need to have some definitions. And so this is a quite simple section, 5.1, where we're going to define what we mean by the mass flow rate and the volume flow rate. And we're going to apply this to flow rate equations and describe how the flow rate equations are derived. These are pretty easy equations. And we're going to define and calculate the mean velocity. And in this case, it'll be the area weighted mean velocity. So let's get going. So there are two ways to characterize the rate of flow. One is through what's called Q, the volume flow rate, and we'll be using Q quite a bit in the rest of the semester. And also an alternative way is the mass flow rate, which we give the symbol m dot, which is just really, it's really dm dt is equal to m dot. So it's just the rate of change of mass and time. So let's take the volume flow rate first. This is just a change in volume with respect to time. Now there should be an E there. With respect to time at any instant in time. So if we look at the definition here, we have Q equaling the volume that's passing through a cross-sectional area. It might be the cross-sectional area of a pipe or a channel for a given interval in time. And so if we look at it in terms of calculus, we're going to take the limit of delta t as delta t goes to 0 of the change in volume over the change in time. Flow rate, and this is important, flow rate is synonymous with the term discharge. So engineers a lot of times use the term discharge, and so these two terms, volume flow rate and discharge, will be used interchangeably. So this example figure from the book just describes how one might go about determining the flow rate. And so here's a gas pump, a gas handle, and we know that gasoline comes out of this pipe here, and a convenient cross-sectional area to define is just the end of the pipe. And so we'd be interested in the volume of gasoline that's passing per unit of time outside of that, from within and out of that nozzle, basically. Another example is just someone's mouth, the cross-sectional area being your mouth, and how you breathe. You breathe in air and out air through that cross-sectional area. So Q again is just the volume per time. So when we look at the equations a little bit more closely, we can see that we can rewrite if we have uniform velocity, and so we have a uniform velocity field here. We can see that we can rewrite the volume as the area times the velocity times delta t, where basically the velocity, don't get confused now by the volume with the line through it and the velocity v. Those are two different things. But in this case, the velocity of the fluid times the time is just going to equal some distance d. So you can imagine that we have a cross-sectional area here in this pipe, and then at some certain time, a certain amount of that fluid passes, and that gives us a volume. It basically gives us the length of that volume, v dt, the velocity times the time. Note that the units of velocity times time are distance. So the units of this are volume, a times the velocity times delta t. So in the case of a uniform velocity field, we actually can cancel the delta t's out, and we have this result down here that the volume flow rate is just equal to the velocity of the flow times the area. And note the units. The units of volume flow rate are basically volume, meters cubed or length cubed over time over seconds. And so when we multiply velocity in meters per second times area, we get these units of meters cubed over seconds. Now, we can generalize that a bit. We don't always have a uniform flow. So let's assume that we have a flow going through a pipe that actually has some sort of parabolic shape to it, that the velocity in the center along the center line is actually faster than that on the edges, perhaps because we have shear stress along the side between the fluid flow and the pipe that is slowing down the fluid to the velocity of the wall there through the no slip condition. So if we do have viscous effects, we're going to have a non-uniform flow field. And all we have to do in this case is to define a differential area here with a length and a dA. So again, the length of this is going to be VDA. And we're going to be able to sum up all these individual pieces to give us the amount of flow going through. So instead of this being a constant v times a, we actually have to integrate the velocity over each individual area element. So it's a little bit more complicated when we have a non-uniform flow. And we might have to integrate. Now, in the most general case, the velocity, here's the velocity, the general velocity vector. The velocity vector may not even be normal to the area that the cross-sectional area that we're interested in. And in that case, we would have to determine the dot product to determine the flow rate through this surface. So in that case, in the most general case, we have the velocity field dotted with the dA, and so basically we're finding the component. If you remember from maybe your vector calculus here, that the vector v dot dA is going to be v dA cosine of theta, which is just basically the projection of the velocity vector in the direction of dA. So we're accounting, that's the cosine of v. It's basically, here's a better way to write it, v cosine theta. So it's the cosine component, if you will, of the velocity through that differential area. So in the more general case, the most general case, we're going to have this equation here. To be quite honest, a lot of the problems that we solve are going to be able to use this simplification. If we'd have uniform flow, things are a lot easier. Now, we also make a definition here of the mean velocity. The book talks a little bit about this. It's important to note that this is a different type of mean velocity when we're talking about the volume flow rate. Because we are actually, it's an area weighted velocity. So we're taking the integral, instead of taking the integral of the velocity with respect to time and dividing by time, which it gives us a time average. This would be a time average. This is an area weighted average velocity because we're integrating over area and then we're dividing by the total area here, 1 over a. So this is an area weighted mean velocity, and so this is sometimes used when trying to understand volume flow rates. Now the other definition, so that's Q, and if we look now towards the mass flow rate, this is a very similar thing. As I mentioned, um, this is the mass of a fluid crossing through some cross-sectional area in an interval of time, and it's just the change in mass over the change in time. But look at what we can do here. We can rewrite delta M as the density, assuming constant density. If the density is constant in our flow, then we have the limit as time goes to zero, the change in volume over the change in T, which is just our value of Q. So when we have uniform flow, we get a simple equation for the mass flow rate of just basically density times Q. So really, it just depends on what our problem is, whether it's more convenient to talk about m dot or Q, but they only differ by having the density in there. M dot is just the density times Q. So in general, in the most general case, you're just going to have the density being multiplied by this dot product that we had here, the most general, I'm sorry, right here, the most general case for Q. So we have these two definitions, and table 5.2 summarizes them. Here it is the equation for the volume flow rate. It's just equal to this average velocity in general, the average velocity times area. That's also equal to m dot, the mass flow rate, over the density, as we just saw. And these are the two equations. This is the most general form here with the dot product in it. And we've got all the different pieces are defined over here. And then down here, we've got the mass flow rate, which is m dot times rho a times the average velocity, if we're in the area average velocity. That can be written as rho q, as we saw, just the density times the volume flow rate. And in the most general case, we have the density multiplying the dot product of the velocity times the differential area element that we're using to integrate over our cross-sectional area. The only other thing to say, the last slide in this section, is when the velocity varies at different points on the area, or what we're going to begin to call the control surface. The cross-sectional area is normally the control surface. We have to define a differential area element, and it's very important to choose that dA carefully. So table 5.3 gives us a couple of different options. We've got channel flow and pipe flow. In the case of a channel, when the velocity varies as a function of y, so it might vary as you go up. It might be it might be slow down here, getting faster, and then slow again. We'd have some profile of velocity in the y direction. It might look, just to give you an example, it might look, the velocity profile might look something like this in y. I don't know, but it has some shape to it. So the most logical differential element to choose is dA equal to the width times dy, because we have to have y being the differential element because the velocity is varying in y. Alternatively, if we have a pipe which has some sort of radial velocity variation, so in this case v is varying as a function just of r, the radius of the pipe. It might be fast flow in the center, getting slower as we go out into the edge of the pipe. Then we would use basically a differential area dA, which is basically an annular ring. So we have the circumference, 2 pi times the radius, that's the circumference, times dr, which is basically the thickness of this little annular ring, and we would integrate that differential element from 0 to the maximum, to the wall, to the pipe wall. And r is basically the radius of the differential area element, and dr is the differential radius right here. So so that's it for this chapter. To wrap up, we really need to understand these equations: the volume flow rate and the mass flow rate. And remember that they're very similar, only that the mass flow rate, you just multiply the volume flow rate by the density. Okay, thanks.